Welcome to the Week 8 lecture for Microprocessors and Robotics.
This week we're going to be focusing on integrating push buttons into our circuits and microcontrollers. So we'll be looking at how to do that, how we are using a pull up and a pull down to integrate those push buttons, the if-else commands that we need to program those push buttons, and then we'll see how we built the circuit to physically integrate them.
Towards the very beginning of the course, we talked about the difference between digital and analog. So as a refresher, digital is either one value or another, right? It's high or it's low. There's no in between. Analog has kind of a range that it can fluctuate in between. There's not really one stopping point for it. So we can try to break analog down into different numbers, which we'll do later on. When we're fading, I believe we have the values between 0 and 255 to work with. So we've broken it down into discrete values, but we're still trying to assign values to essentially an infinite curve here, right? Theoretically, you could do 100.5, right? 100.52, 100.523, and so on and so on. So analog is a wave that can vary at any point. It doesn't have defined values necessarily. It can be defined infinitely. But digital is either high or low. It's a 1 or a 0. It's not 1.2345 or 1.4567. Digital is essentially high or low. It's a discrete signal. And so we've used digital right to turn our LEDs on and off, right? That's been very clear. They've either been on or they've been off. But we can use an analog command. We can use analog right to fade an LED and give it a level of brightness somewhere in between on or off. And so we'll take a look at how we can do that using our analog right command. So unlike digital right that tells a pin to either be high or low, analog right tells a pin to be at a specific intermediate value until it gets another command, or a specific duty cycle until this is replaced by something else. Just like in digital right, we would be telling a pin to be high or on until we told it to do something else. So analog right is telling this pin to be somewhere in between high and low. And I kept harping on the pin map, right? Note which pins can be used for which inputs and outputs. And when we get into analog right, this is certainly the case. So you'll want to refer back to the pin map and note which pins that you can use as analog right pins, because we can't use all of the pins on our microcontroller as analog right, only certain ones. So if you try to use a pin that's not analog right, it won't work. So just refer to the pin map, figure out which pins you can use, and you should be just fine. So when we use analog right, it's a little bit more complex than digital right. When we're using digital right, we're just specifying a pin and then either high or low after the command, right? So analog is kind of similar to that, but we need a little bit more context to make it function efficiently. And so just like the digital write, it does need to know which pin that it's supposed to write to. It has to know which pin to activate, but then it needs to know what we call the PWM, or the pulse width modulation value, to fade to. So instead of just an on or an off, we have a range of values that we can select when we're using our analog write command. So our pulse width modulation, or PWM, is what we use to control what we call our fade amount. So it's just a value between 0 and 255, 0 essentially being off, or 255 being all the way on. So an easy way to see this value is the brightness of an LED. We would know that if it's somewhere around 125, that's kind of the midpoint for an LED. It'll be right in the middle of on and off, so it will be a little bit dim. And this can absolutely be used with other components. We can operate them halfway or at halfway on, so to speak, but an LED is a really good way to illustrate this. It provides a really visual reference for you to see, and it's a good indicator of if the LED is being analog written to a low value or a high value, or somewhere in between. So we want to have a pin and we want to have a fade amount when we're using analog write. So we specify our fade amount by pulse width modulation, and we give this a number. And again, it can be any value between 0 and 255. 255 is all the way on, 0 is all the way off. And so we'll look at how to put these together. It is important to note that when you're using analog write, it can change the value very quickly if you have multiple analog writes in a row or depending on how your code is set up. So sometimes for us to see that fade, we would need to integrate delays. So if you had a pulse width modulation that counted up very quickly from 0 to 255, if it went 1, 2, 3, 4, 5, 6, and so on, all the way from 0 to 255, it would almost look like the LED was just turning on because that fade would happen so quickly. So if we need to see that visually, sometimes we have to introduce delays so that we can see the fade. So I think when we take a look at the code, that will help provide a little bit more context of how we would set up an analog write command. So in the first part of our code, we're going to set up a couple of variables before we start. And the first one is going to be an integer. It's just going to be a number. And the second one is going to be an integer as well. But the first one we're going to call brightness. And that's how bright our LED is going to start out at. And so you can see that we're starting it out at a value of 0 or off, right? There's no light being emitted. And then the second value that we're going to specify is our fade amount. So how many points at a time we're going to fade the LED by, and that's going to be 5 points at a time. We could do it 1 point at a time if we wanted, but we're going to start out with fading in 5-point increments. In the next part of our code, the setup part, we're going to declare pin 14 to be an output. So pin 14 can be utilized as an analog pin. So just like any other time we're declaring a pin as an output, we're going to declare pin mode. And here I've used the word green LED, but you could also certainly just write the number 14, or you could declare pin 14 earlier on in the code if you wanted to and give that a name. But so we're just declaring pin 14 or green LED to be an output. So that's the first thing that we need to do in order to get this to work, right? We have to set our pins to be outputs. And here's the main loop of our program where we're starting to use our analog write command. So we start our void loop and we use our analog write to set the brightness of our green LED. So our green LED is going to be the brightness that we already established. So if you'll remember, we're going to start out with our brightness at 0. And our fade amount was equal to 5. And so in the next line, we see a little bit of math going on here. So we're saying that the new brightness is going to be equal to the old brightness plus the fade amount. So if I go in and write these, the initial brightness is 5 plus a fade amount of 5. And so all this means is that every time we loop through, we're going to be incrementing the brightness in amounts of 5 on the PWM. So every time this goes through, next time the brightness will be 5. So it'll be 5 plus 5 is 10, 10 plus 5 is 15, and so on. So this little equation here will keep increasing the brightness. Then on this next line, I'm not going to get into this command too much, but it is saying that if the brightness value is equal to 0, or if it is equal to 255, you'll see we have a little OR gate in here. If it's equal to one of these values, the fade amount will equal a negative fade amount. So all that means is we're going to put a negative in front of the 5. And so we're going to start at 0, right? Our brightness will start at 0. It will keep going up by 5 until we hit 255. Well, then what? The LED is just all the way on, right? So how do we get it to fade off? We do that by making our fade amount negative. So that makes this a negative 5. And so what would happen when we loop through is we would then have 255 plus a negative 5. So then we would go down to 250, right? And then the next time we loop through, it would be 245. And so it's reversing that fade amount. And then when we met this condition and we hit 0, it's going to flip the fade amount again, right? Two negatives cancel each other out. So it becomes a positive 5 again. So then we start with 0 and we're adding 5 all the way back up. So this if or line down here, I'll re-highlight these. These two lines down here are just saying that when the brightness reaches the threshold, we're going to change our fade amount so that it goes the other direction. And then before I talked about how we might need a delay to be able to see the effects of our analog write and our PWM changes. So I'm just implementing a 30 millisecond delay after each fade increment of 5. And so this will keep looping. We'll keep setting the pin to the brightness, right? That's what our analog write command is doing again and again. So it's setting the brightness. We are adding 5 to the brightness. If we haven't reached our limit, we're going to wait 30 milliseconds, and then we're going to keep going. So we're going to then set the brightness to 5, add 5 to it, which would be 10. We haven't hit a limit. So then we're going to wait 30 seconds. Then the LED will be bumped up to a brightness of 10. And then we're going to add 5 more, and so the loop's just going to continue until we hit one of these thresholds, and then it will go down the other way. So this is your example. This is how we would set up a fading code. So you don't need the equations, you don't need the brightness equals brightness plus fade amount, you don't need the if commands to use analog write. If you wanted to get really simple, just like we've turned a pin on and off, you could assign this brightness section to be any value that you wanted between 0 and 255. We're just implementing some additional coding to help work in a fade so we can see the capabilities of the analog write command.
Typically, push buttons are used to turn different components on and off. This illustration is just a simple LED, again, because this is easy to recognize what's happening. So in this circuit, we have our power source, our battery, we have a push button up at the top. On the right side, we have a resistor, and on the bottom, we have an LED. And so unfortunately, the animation is lost because there's a recording along with this slide. But in the animation, you would be able to see, oh, there we go. It is working, great. So you can see that when the button is making contact, it's actually closing the circuit and allowing the LED or whatever component is at the bottom to turn on. And of course, when the push button is up, when it's not being depressed, the circuit has a gap in it. Right here is a gap. And so if there's a gap in the circuit, then the current can't flow and nothing will happen. So by pressing that push button, you are completing that gap and allowing whatever component is connected to it to turn on. And so the way that we do this in our programming is with the command of button state. And so this is reading the state of the button. So we have button state, we're going to have a digital read, button state equals digital read, and then this last variable button name, this can be whatever you're calling your push button. So if you have it connected to pin 14, you could technically put a 14 in these parentheses. Of course, good practice is to give your variables names at the beginning of the program, declare your variables. That way, if you ever need to change that pin number, you only have to do it in one spot up at the top. And so at the top of our program, we would have something like button name equals 14 to identify which pin of your microcontroller this would be connected to. But whenever you're programming, you want to use button state to pull to digital read the push button. So this is the programming format that we're going to use. So we've talked about pull-ups a little bit in previous lectures, but when we're using a push button especially, we also need to use a pull-up in conjunction with it. So in addition to declaring the variable of that pin and giving it a name, we also in our setup need to give it a pin mode. So our pin mode is just going to be whatever label we give the push button, and then this command input pull up here is going to set any input connected as a pull up resistor. And the reason we do that is if we don't, it can be hard to determine the state of the pin. It could detect a small amount of voltage, and that could mess with the logic determining is the button being pressed or not. And so we set it as an input pull up to kind of filter out some of that noise. That way we can make sure that when we're really pressing it, that's what the circuit is detecting, or your microcontroller is detecting, that it's only detecting a press if you're actually pressing it. And if you're not pressing it, then it shouldn't be detecting anything. So by using this input pull up command in our setup, this is acting as a filter. The interesting thing about this is it makes the push button work the opposite of how you would imagine we think it would. So typically, we refer to our push buttons as either in a high or a low state, kind of like our LEDs. So if it's on or if the push button is pushed, it's in a high state, is what you would assume. And then if it's not being pushed, there's no current flowing through, or in an LED case, the LED would be off. We would think of that as low. But because we're using an input pull-up, it actually flip-flops these high and low assignments for our push button. So when you're not pressing it, it will be sending a high signal, and when you do press it, it will send a low signal. So when you're programming your push button, just keep that in mind. It's a little bit of counterintuitive, just because we're using the input pull-up to act as our filter. So I've already went over most of the code for the button state command, but I will go over it again just to hopefully cement it in your minds. So this is our button state command right here. Lowercase b, capital S is typically how we write it. Then just an equal sign, and then we have a digital read. So we use digital write to send an output signal to an LED to turn it on or off. But in the case of a push button, we need to read that signal to detect if it's being pushed or not. So instead of a digital write, we're going to use a digital read command. And then in parentheses is just the label, whatever you've called your push button. In the beginning, you should have assigned some sort of label to that pin number that your push button is connected to. And so what this line does is it checks if the button is pressed or not, because that's important. The code presumably needs to know if the button's pressed, and then it can perform certain actions based on if the button's pressed or not. And then so again, just because of our pull-up resistor, if the button state, if it reads the input as high, so we're doing a digital read, it will read the button state as either high or low. And if it reads it as high, that means the push button is not being pressed. And if it reads the button state as low, that means that it is being pressed. So normally in conjunction with integrating a push button, we're going to use an if-else command. So we're using a push button because we want it to trigger some other activity. So we're saying if the button is pushed, then this should happen. And so this code is what allows us to do that. And so we have two different code types here. So this first one at the top, these two lines, or these three lines rather, this is just an if command. So this is saying if some condition happens, then we would put other coding down here to make something happen. So if the push button is on, then this stuff should happen. We can also do an if-else command. So we can say, similar to the if command, right? If something happens, then do this, or else do this. So it gives an alternative. So it's saying if the button isn't being pushed, then this should be the state. So if we would fill in these blanks and say if the push button is low, right, that would mean it's being pushed. If the push button is being pushed, turn the light on. And so we could fill this in. The only drawback to that is that we could let go of the push button and the light would stay on. There would be no code telling it to turn off unless you had it stayed on and then you gave it a delay and then you had it turn off. So you could put it on a timer if you wanted, but you would have to work that into your if code. Another way to do this is to say down here by using an if-else command, we can say if the push button is pressed, then turn the LED on, or else turn it off. And that's what you'll see in your lab assignment here in a few minutes. So we'll be saying if you're pushing the button, then the LED should be on. If the button is not pushed, then the LED should be turned off. No timing, no nothing. It's either just on or off based on the state of the push button. And so for that, we need an if-else command. And so in these commands, we talked about having a condition, right? So we're saying if the push button is on. Well, how do we say that? We can't just write those words in the code and say if the push button is on. What we would do is we would say if the button state is equal to low, right? Because low is the condition that the button is being pressed in. And so we would use these two equal signs up here as part of our logic. And you can see this example over here. So A is equal to B. This is checking if these two comparisons are equal, or these two operands, or whatever you'd like to call them, are equal, these two inputs rather. So is the button state equal to low? So that's what we would be checking in this code. We also have some other options that we can put in here. If we put an exclamation mark and then an equal sign, this means not equal. So if we want to make sure that two values are not equal, we could do that. We could do a less than, a greater than, a less than or equal to, a greater than or equal to. And so you can use if-else commands for other things outside of push buttons. They're not limited to that. You could use it to check other inputs, see if they're equal to a certain number or something like that. But for this lab, we're going to keep it simple. We're just going to use checking if the input is equal to low, which indicates that the button is being pushed. So here's the code that is part of your lab, and I can't give a complete code without essentially giving you the answers to your lab, but we can step through the pieces of this code, and I think that'll help make things pretty clear. So in this first line here, we are going to declare or give our push button a name. This is where we're assigning our variable names. And so here I've used push2. Remember, we used push2. That is correlated to pin 1.3. Our pin, I believe it's 14 if you have the EX microcontroller model. So we can use any of those if you didn't want to put push2 there, but you need to identify it with a label. The next line, we're just assigning a label to our LED that's connected. So in this program, we're assuming we have a push button and an LED. And so we're giving our LED a pin number. And then we are also declaring our button state, our push button state, to start out as 0. So you want to always do that to kind of clear the button state. Then in our void setup, we've done this before. We're just initializing the LED pin as an output. So I'm not going to give that away because you've done that before. You should be able to fill in that blank, but this is where we're defining what things are. So we're going to define the LED pin as an output, and then we need to define our push button pin as an input, and we're going to use the input pull up. Oops. That just covered that up completely. We're going to use the input pull up to help you out there. And I think if you go back a couple slides, you'll see the terminology that we need to use to declare our push button pin as an input. All right, and so next we start in our void loop, and the first thing to do is detect, is the button being pushed or not? So this first line I've given you, and it's just saying that the button state is equal to figure out the button state, we need to digital read whatever variable you've decided to call your push button. So here I'm assuming you've called it button pin. You can change this if you want. Just make sure what's in these parentheses matches up here. So make sure those two match. Fill in your parentheses with whatever label you've called your push pin or your push button. And so this line is going to read the state of the push button, and it's going to store that value in the button state. All right, the next thing to do is a little comparison. So we're going to say if the button state, this should be low, not high. I did correct that on your labs, but that did not make it into the PowerPoint. So this should say if the button state is low, then you will fill in this blank here. We'll turn the LED on. So you'll input whatever line of code turns the LED on. And then we're saying or else turn the LED off. So whatever code you need to turn the LED off here, you will be filling in. So you can see how we're declaring all of our variables, we're digital reading in the state of the button, and then we're comparing it. We're saying, is the state low? Is it high? What is it? If it is equal to low, then we should do this, turn the LED on, or else, if it's not, we should do this other action and turn the LED off. So this is your basic structure for setting up a push button with an if-else command. That way you're detecting the state of the button and then actions are resulting from that. Okay, so we've talked about how to integrate a push button and how we would typically program that with C language. Now we're going to take a look at how do we physically integrate a push button into our circuit, because in this lab you'll be constructing some basic circuits. So if you'll notice, this push button has 4 legs, so to speak, coming out of it. Right, like a resistor and an LED would typically only have 2 push buttons. They have 4. So because of that, you're going to want to make sure that they're spanning this bridge in the middle of your board, because remember, all of these are connected on your breadboard and all of these pin inputs are connected on your breadboard, but they are not connected to each other, right? These 2 rows are kept separate. So you need to span your push button in between this middle section so that each corner has its own row. So you're going to plug it in over the middle section, bridge that gap, and then we're going to do some things to different corners. So this top left corner up here, we're going to connect to our power source. We have to have power running through this. And so you'll see here is our power pin up on our board. It's running through the wire into this row. And then we're also connecting a resistor as a buffer between our power source and our push button so that the current is not too high. So you're going to have your resistor, and then your resistor is going to be connected to one corner of your push button. The top right corner, you can see pretty clearly, we need to ground a corner of our push button. And so quite simply, if we follow the ground wire, this just comes back into the ground pin of our board. And your board might be laid out a little bit different, but just find the pins labeled as the power source. Sometimes it will say 5 volts, and then find the one labeled as ground. So our third pin will be the pin that we're reading from to check if the button is pressed or not. So we have a power source, our pin is grounded. Now we need a way to read it. So what we're going to do is connect our third bottom left corner to a pin. And here I have it connected to pin 1.3 just because it is the same as our board push button. And I'll get into why in a second. But so that's really all you need. You need a power source on one corner, a ground on the other, and then the third corner should be connected to a pin so that this is where we'll read if it's high or low. And then we don't really do anything with the fourth corner. We can just leave that alone. So when you're building your circuit, keep that in mind. Your setup should essentially look like this. So what we just looked at was a picture representation of your push button setup. This is just a circuit representation. So you can see we have our push button here. This is all our button. And you can see it kind of looks like it's the representation for a switch. So when it's open, it's not being pressed. There's no current flowing. If it's closed, the current can flow. And so we have our 4 corners here. So on our first corner, we'll look at this one. Top right, you'll see we have this connected to a resistor and then it's connected to our power source. This bottom right corner is grounded and then the top left corner is connected to our pin 1.3. So this is the exact same thing as the picture that we just looked at, but in diagram form. This representation here, you'll notice it's using an Arduino board, but it's essentially the same setup as it would be for a launch pad. And here we have 5 different push buttons connected. So you can see that all of them have their top left corners connected by the green wires to a pin. And this is where we'll read their inputs into the code, and you'll also notice that their bottom left corners, those are all being grounded. And then the bottom right are all connected to the power source. So this is just how we would connect multiple push buttons. You may notice something different on this one is that the resistors are connected on the ground side instead of the power side. So in the last example, we had the resistor between the power source and the push button. This example, it's between the ground and the push button. You can do it either way. Best practice is really to put it between the power source and your push button. But essentially it doesn't really matter in our small circuits as long as you have a resistor on one of those sides. So you can see this is laid out all nice and neat. This would probably be one of the best ways if you had to lay out multiple push buttons. All right, this diagram here is showing us what we need to do if we want to connect both a push button and an LED to our circuit. So in our push button, you can see top right corner is connected by the orange wire to pin number 8. Bottom right corner, we have a resistor and then connected to ground. So you can see we're doing kind of an intermediate connection. We have a wire coming across to our ground rail, and then we have our main connection running all those over to ground on the board. And then the bottom left corner of our push button is connected to our power source off the board. So we have our push button connected like normal, and then we're just going to connect an LED like we normally would. And so the shorter leg is grounded. Remember, shorter, negative, and so that's the one that's going to be grounded. So here, ideally, you put a little wire, kind of like we did on the resistor over here, in between the little pins, the row of pins, and the ground. But here they've just directly connected the LED to the ground, which is fine, but not preferable. And the positive side, they've added a resistor. This is important to add a resistor in between the LED and the pin it's connected to. So we have our positive side of the LED with a resistor and then connected to the pin that it's going to be based off of, and then the other side is just grounded. So these are essentially not tied together on the board. Your push button and LED aren't really tied together. They're just set up like you would if you were setting them up all by themselves. And so this is just another diagram of another different way to set things up. On this board, we have a single push button, of course, top right corner connected to the pin that we'll use to read the status. Bottom left is connected to the power source, and bottom right with a resistor in between is connected to ground. And then we see we have 3 LEDs on the board. And so their short sides on the right, those are all grounded. You can see those by the red, yellow, and green wires at the top. Those are grounding the LEDs. And then down on the longer side on the left, they have a resistor in between, and then they're being all connected over to pins. So this is another really nice and neat way to set your board up if you're integrating a push button and multiple LEDs. This is just to kind of explain how we would incorporate multiple components together on a board. If you had multiple push buttons, you needed multiple LEDs to kind of help kickstart thinking about your project and how you would connect and rearrange things. So now that we've gone through the commands for integrating a push button and kind of the basics of where things should go on the board, I want to do an actual walkthrough on how to build a circuit. I typically don't do this for my in-person class, but I want to make sure that this isn't a hang-up for you because when you're in class in person, it's easier for me to walk around the room and help you troubleshoot. If you have a misplaced wire or a backwards component or something like that, online that's a little bit more difficult. Not impossible. If you send photos and really good descriptions, we can figure out what's going on still. But I think it will be a lot easier if I kind of walk through the typical setup for integrating a push button and an LED into your circuit setup. Just to rule out that, because this class is not necessarily about how well can you build a circuit. That's important if you can build a basic circuit. That'll really help your final project, but this is mostly about programming and exploring the features and possibilities of a microcontroller. So we'll get into it. So right here, I have a microcontroller set up with my push button program. You can see I'm using the integrated push button to turn on the integrated LED. So everything's in the board. So what I'm going to do first is add an external push button. It'll run off the same program, but we'll be adding an external push button this time. So I'm going to add it to my board. I'm going to span that bridge. These can be kind of hard to put in place because the wires are a little bit short, so make sure it's really well secured in there. It's clicked into the breadboard. And notice how it's kind of spanning that bridge, right? So the rows of 5 pins on each side are not connected. That's very important to keep all 4 pins of your push buttons separate. So make sure you're spanning that gap and that it's pushed really well into your board. So I'm going to add my ground and power wires just so I have ground and power going down those strips alongside of the board. So everything in that strip then it can be connected to ground and power. So I'm not connecting anything to my microcontroller yet, just getting stuff set up on my breadboard. All right, so the next thing we're going to do is ground one corner of my push button. So I'm just plugging that into my ground rail, and then I'm going to add power to another corner of my push button, but before I do that I need to add in a resistor. So I'm just going to pop in a little resistor, again in line with one of those corners of the push button. Sometimes these components can be kind of hard to put in the board, so just wiggle it around a little bit and make sure it's clicked in there. So I have that resistor on one corner of my push button, and then I'm adding power on the other end of the resistor. I'm plugging it into the power strip alongside of the board. And then lastly, I'll be adding a wire to the third corner of the push button, and this will connect to my pin, my actual pin number. So when I turn over the board, you can see everything is labeled underneath. That's where we'll be plugging our wires in. So first I'm going to plug in my push button to pin 1.3 because that's the same pin that we used to program the push button on the board. So we're going to use the same one so we don't complicate things. I'm going to plug in my ground wire, and I will plug in my power wire. All right. So now this is my setup for plugging in one push button, getting everything set up, and now we'll go ahead and test this and see if it works. And so we can see it does. Hitting this push button does light up the red LED on the board, and the push button on the board also lights up the LED. So I mentioned that I plugged the pin into, or the push button into pin 1.3, same as the pin connection to the push button on the board. This helps with troubleshooting. So the reason I do this is to make sure that nothing is wrong with my code. Because if I plugged this push button into another pin and something wouldn't work, I wouldn't know if I had coded something wrong or if something was wrong with my circuit. So we have an advantage here because this is so simple. We already have a push button and LED on our board. So I can run through my code first and make sure that works using the board components. And then by connecting the external components to the same pins, I can verify that my circuit is built correctly. And then at that point, if you need to, or if you want to, then you could change which pins things are connected to. But so it's a really good way to test things out and making sure separately that your code is good, that your circuit is built the way it should be, and then you can put those two pieces together. So I always try to connect things to, again, the pins that they're labeled as, so that they're the same pin labels as the integrated components. Okay, now I'm going to add an LED to my board, and if you'll remember, the short side we connect to the ground. So remember, short side, negative, we ground that. So I'll span it between two different rows. The short side I'll go ahead and add to my ground rail. And then to the long side, I will not directly connect to anything before I add a resistor. So you always want to add a resistor in to your LED. So I got my resistor entered in there, and then I'm going to add another wire to connect this to pin 1.6 because pin 1.6 is the same pin as our internal LED. So that means they'll both light up, which is fine if we assembled the breadboard correctly. So I hit that push button, we can see they both light up. So what would happen if the board LED was lighting up but not your external LED? That would mean you probably wired something wrong on your breadboard. So that's why it's good to use the same pin numbers. Another word of caution is when you're connecting your LEDs, don't forget to put in those resistors. Add those in between the LED and either the power or the ground. And I know I've already mentioned this, but if you don't, you will ruin your components. So that's another tip, is if a component seems to not be working, you can't get your circuit to work right, try swapping it out for another one. Especially if you're working with components that are in the Kent Tusk lab, or if you're borrowing components, anything like that, they could have been destroyed or short-circuited without you knowing about it. And so sometimes you might just need to swap out an LED for another, or a resistor for a different one, and that will solve your problem. So that concludes how to integrate a push button and an external LED into your board. Again, you can change the pin numbers that these are connected to and change the pin numbers in your program. That's fine, but I do recommend that you keep them matched up to the same pin numbers as the external components to help as you're learning this process, this assembly, and working with a microcontroller and breadboard. So of course, if you have any questions, absolutely email me. Pictures are always helpful if you're having trouble with the way things are connected. I would recommend when you're building your circuits, you can see I've used all black wires for anything relating to grounding, all red for power, and then other colors for various components. But general good practice is to use those black and red wires for grounding and power respectively. And then just try to keep your board nice and neat so you don't have wires running everywhere. Now we'll go ahead and review what is in your Lab 5 assignment. So you have essentially two objectives for Lab 5. The first is fading an external LED, and the second is controlling an LED with a push button, or essentially being introduced to using push buttons. So there's 4 parts to this lab. Part 1 is fading an external LED. So I've given you a diagram to follow, both a physical representation on the left of your board and what that circuit should look like, and also the diagram on the right. So again, these are the same thing, just in 2 different forms. So I've given you the schematic and a reminder, and I've also given you most of the code that you'll need. So you may have to make a couple edits to this code. You may want to change this pin to a different pin. If you really wanted to, you could change the brightness and fade amounts. But I've essentially given you most of the code that you'll need, with potentially a few tweaks to get this going. So this will fade that external LED if you have the LED connected correctly. So when I'm doing these labs, this one and as well as later on, you'll see the first essentially introduction to it. I've given you sort of a sample code to test out and just confirm that your system works. You can look through the code and you should be understanding how each piece works. And then later on in the lab, I'll ask you to change things about the code or to add more to it to cement your understanding, and that's where your hands-on work and understanding comes into play. Okay, so part B, I ask what we would change in this program to fade the LED faster. You don't have to make that change. I'm just asking you what would we need to change to make that fade happen at a faster rate. Now, in part C, I am asking you to change the program with some specific instructions. So I want you to make the LED fade more slowly, and I give you a specific delay and a brightness range. So you should be able to figure out how to change the code to meet those parameters, and then document those changes. In part 2, this is where it comes in that you now demonstrate your understanding of the concepts. You're going to fade 2 LEDs. So here I do not give you a diagram or the additional code. That's on your part to figure that out. But what you're going to do is connect a second external LED to another pin, and then you're going to program that to fade your LEDs in a pattern of your choosing. So they could fade at different speeds, they could alternate,
that you can essentially do whatever you want. I just ask that you don't fade them in the exact same pattern at the same time. So they should be operating on two different patterns, not the same one. And then you're just going to record a short video of that of your LEDs fading and submit that with your lab. And let me pop back up here to this first part real quick. So in part A, I ask you to record a short video of your LEDs fading. You can disregard that. I'm going to take that out when I actually upload this lab. I don't need a video of part A, but I do ask you to take one for part 2. So that can just be, by whatever means necessary. Just get that short clip of your LEDs fading and running through your code, and then just upload that little video snippet with your lab. In part 3, we start to get into our push button programming. So here again, I'm essentially giving you a little bit of an example with a couple blanks to fill in. So what we're going to do is start with an integrated push button, and this just makes sure that you have your program right, you're understanding what goes in those highlighted areas, and how to get that set up correctly before we add the external components. So you're just going to use this code, fill in the blanks that I've highlighted here, and I've given you some hints with some comments. So you're going to fill this in and blink the integrated LED with an integrated push button. Pretty straightforward. Part 4, again, this is where you're mostly on your own here now to show that you understand the concepts. I have given you a schematic below. So here you're going to use an external push button to blink that internal LED. Now I've given you a diagram and I do have a note up here that I want to cover. So in the diagram, you'll notice this is not an Arduino board. This is actually a MSP Launchpad board. The reason that I'm using this image instead of one that's Arduino specific is because I like this better. I think it's a much simpler depiction of how to install a push button compared to what's out there showing the same thing on an Arduino board for some reason. Not quite sure why that is, but I like this image best, so I've chosen to use it. What is important to you, what will be important, is just to recognize that these pin locations will not be the exact same as on your Arduino, right? So these are you can see some ground pins down here. Those may not be in that exact location on your Arduino board. But what you can do, so I'll go over these one by one. This black wire is going to ground, that's GND on the board. And you can also look back at the lecture for this week too if you need some clarification on where the various wires should go and how you should be setting up a push button, but I think this should be plenty. So this black wire is being grounded. So again, any ground pin on your Arduino board is suitable. This red wire is going to a power source. So the Arduino power source may not be down here. I don't believe it's the pin on the bottom right corner, but wherever the power pin is, the VCC on your Arduino board, you just want to connect to that. And then this blue wire here is connecting the push button to a pin. So here it's connected to pin 1.3. You can connect it to any pin on your board that is a digital read pin, right? It needs to at least be a digital read to read the input coming in from your push button. So just bear that in mind. And I also like this too as another exercise of helping students be adaptable so that if you were to see a diagram of something set up on another microcontroller, you would be able to interpret that and figure out how to adapt it to the microcontroller that you have. So a good lesson in adaptation and understanding the concept behind things and how to make those tweaks and changes so that it fits your specific system. So again, your pin locations may not be in the exact same spot as this microcontroller here, but essentially just make sure that you are connecting to a ground, a power source, and a pin. Okay, once you get your external push button connected and working, I want you to then go on to the next step and add an external LED to your circuit. So I have you doing these separately. Again, it helps troubleshooting. That way, if something's not working, you're not trying to figure out if it's the push button or the LED. In A, you've already got your push button working. So you know that, okay, now the next step is the LED and you can focus on that. So here I have you adding an external LED to your circuit, and then you'll just make any changes that you need to your program so that it works with that external LED and the external push button. So what you should see, if everything is working correctly, is that when the push button is pushed, the LED should turn on, and when the button is released, the LED should turn off. And I do ask that you include your program below here in the lab report. And then lastly, you're just going to write any observations that you made in this lab and a short summary of the concepts used. And so to expound on this a little bit more, in general, I've seen mostly good responses to this question. But if you've received maybe some points off for this question, let me give you a little bit better idea of what I expect here. So when I say observations, I'm looking for what did you see happening in this lab? And that doesn't have to be all positive things. So if you really struggled with a portion of the lab, you can note that. If you struggled with something and figured it out, that's even better. If something was unclear to you and then you discovered the answer, that's great. Or simply, if everything went smoothly, you can write how, connecting a push button to the LED and using certain commands means that you can control the LED. So I'm just asking you essentially what is happening, either what went wrong, what went right, and what did you do? What happened in this lab? And then in conjunction with that, I'm asking for a short summary of the concepts used. And so what I mean by that is you should be able to demonstrate your understanding of the materials. So the lab is one way to test your understanding. And then another way is for you to be able to give a short summary of the concepts. So what new concepts did we learn this week and how did you apply them is essentially what I'm looking for. So I'm really looking here for around at least 4 sentences about a paragraph. Doesn't have to be anything too lengthy, but just some good observations and your short summary of what concepts we're using. So 1 or 2 sentences are not acceptable here. I'm looking for, I would say, around between 4 and 8 sentences. That's not a hard and fast limit, but you should shoot for something like that if you want full points. Okay, and that is everything in Lab 5.0. Of course, if you have any questions, reach out to me and I will get those answered for you as quickly as possible. Or, of course, you can use your other classmates as a resource. Reach out to them and see if they are having the same problem. Are they seeing the same thing? Or maybe they can help walk you through that as well. So lots of resources to get through here. The internet, I will say, is also another great resource. That's part of why I switched over to an Arduino board for this semester, is that there's a lot more content out there online for you to reference. And so you have a lot of options. All right, and that is everything in Lab 5.0.